Welcome to Math with Professor V. In this video, I'm going to break down for you step by step how to find flux using surface integrals. Now, once you learn the divergence theorem, you can also find flux as a triple integral over a solid, but remember that's for closed surfaces. So in all of these situations, I'll show you what to do only working with surface integrals, double integrals. So first of all, our definition for flux, and this is the symbol that we use to represent flux, is it's the surface integral, so double integral over S of f dot ds, and this is a vector quantity. But then actually when we go evaluate it and compute it, it's just double integral over S, so surface integral of f dot n ds. Now I'm going to break down what everything is in this integral, but if you need more of an in-depth video lecture giving you context about flux, then make sure you watch the introductory lesson. I'll link it in the description. So the first thing you're going to do to solve these problems, you're going to draw your surface in 3 space and then its projection over a coordinate plane in 2D. You have to pick, do you want to project it over the XY plane, XZ plane, YZ plane? It really depends on the surface, which one you should choose. So you have to have 2 drawings every time you do these problems. Then you're going to determine what your normal vector n is, and that's always based on the surface, okay? Third, you're going to find f dot n, and you can only have variables that are in your 2D projection. What do I mean by that? If you choose to integrate over the xy plane, for example, if you want to project your surface over the xy plane, then when you find f dot n, it better only involve x's and y's. Remember, surface integrals are double integrals, so you cannot have all 3 variables in the integrand. And then lastly, you're going to integrate, okay? Now, finding n can be tricky, but I'll show you a neat way that I like to think of it that I explained to my class using a little stick figure, and they find it helpful. And then they said these 4 steps really helped them. This is how we did it yesterday in class, so I'm making it for you guys. All right, so find the flux of the vector field F across the surface in the indicated direction. Here's our vector field. Let me just start off rewriting it. It's x to the 5th, y squared, y, and negative z. Our surface S is the portion of the parabolic cylinder z equals 4 minus y squared, for which z is greater than or equal to 0, x is between 2 and 10 inclusive, and direction is outward, away from the xy plane. So that's your standard orientation. Standard orientation is outward from the surface, upward if you're dealing with a plane. Okay, so what I'm gonna do, let us graph. This is y, this is x, this is z. The surface, this parabolic cylinder, 4 minus y squared. Okay, there's 4. Here's 2. And here's negative 2. Those would be the intercepts on the y-axis, yes? Yes. Okay, so here is part of it. Now, since there's no x's in the equation for this parabolic cylinder, that means we take this parabola, downward facing parabola, and we're going to project it parallel to the x-axis. So x, they told me, is between 2 and 10. Oh, interesting. I'm going to scale this axis by 2s. 2, 4, 6, 8, 10. 10, 2. Okay, so let's project now. That looks about right. I'm just going to copy paste this over. One more. Drag, drag, come on now. There we go. One more here. Okay. So, boom. Boom. Now we're gonna, this is 2 right here. This is 2, yes? So the surface really starts here down and goes back there. So we don't have that piece back there. It goes only from 2 to 10. This part up until 10. Good. Let me color it in. So I'll color in what the surface is. It's open. Looks like you took a piece of paper and just kind of curved it around, okay? And then this is the back of it. That's the inside that we're looking at. There's no surface right here. I just drew that to help us get things going. Okay, there's my surface S. Now we need to project it over a plane, and that's what we're going to integrate over. That whatever we project it over, that will determine our base region, basically, that we're going to use to determine our limits of integration for the surface integral. So pick something that's going to be nice. I'm not so excited to project it on the YZ plane. I don't want to integrate over a parabola. I'd rather project this over the XY plane and deal with a cute little rectangle. Can you see how it's just going to be a nice rectangle if we project over the XY plane? Okay, so this is, I should say this is step one. Let me follow my own guidelines. Okay, in the XY plane, it's not perfectly to scale. Please forgive me. So X is going to go between 2 and 10, and Y is going to range between -2 and 2. Interesting, interesting. Okay, but that will be very easy to integrate over. So here's X, here's Y. X is going to go between 2 and 10, and Y will go between -2 and 2. Okay, so this is our base region. So if we're going to integrate over the XY plane, then when I find f dot n, it better only involve x's and y's. Okay, perfect. So let's just write down x is going to go from 2 to 10 and y from -2 to 2. Perfect. Okay, so step 2. Step 2, I need to determine n's orientation. So here's what's going on. We are integrating over the xy plane, over the xy plane. That means my surface here, z, is going to be treated as a function of x and y, which it already is. So for n, I have two options. This is always the case, okay? If it's a function of x and y, then the z coordinate is always going to be either 1 or -1. And then you'll have here partial with respect to x, but it would have the opposite sign of that last coordinate. So negative partial with respect to x, negative partial with respect to y. If this is -1, then you'd have partial with respect to x, partial with respect to y. Okay, how do you know which of the two it is? Well, our standard orientation is outward. So imagine you're standing on the surface, okay? You're standing on the surface. Stand at the extreme point. That will make it clear. You can stand anywhere you want. Your head better point out of the surface, not in the surface. But the easiest way to figure this out is if I'm standing here, I'm out of the surface, right? Which way is my head pointing? In the positive z direction. So the normal vector is going to have +1 where the z component goes. Okay, so then from here I can figure out my normal vector using the surface. It's always normal to the surface. So using z equals 4 minus y squared. So what would n be? Partial with respect to x is 0. Negative partial with respect to y would be +2y, and then z is 1. Okay, so you always have to decide between these two options, and to figure out whether you have +1 or -1, just draw a little stick figure. Your head should be out of the surface, and then figure out if your head is in what is the +1 direction or negative direction. Okay, good. Now that we have n, we're going to follow step 3, which is f dot n, and we're only going to use the variables that are in xy plane, so only x's and y's. Very good. Okay, so 3, we're going to take f dotted with n. Now where was f? F was, I have it up here. Copy. Oops, that was just too much. Let me rewrite it. Okay, f was x to the 5th, y squared, y negative z, dotted with n, 0 to y1. If I dot them, I get 0 plus 2y squared minus z. Uh-oh, we can only have x's and y's. So what do? Well, we replace z with how it's defined on the surface, 4 minus y squared. So this is 2y squared minus 4 plus y squared, which is 3y squared minus 4. Are we good? Okay, then we're ready to go. So step 4, flux is going to be double integral over s of f dot n ds, which is double integral over d. Here's 3y squared minus 4 dA. So the students were asking me, when do you switch s to d? When you switch ds to dA, okay? And then from here, we decided it was just going to be a rectangle, so we're going to stay 2 to 10, negative 2 to 2, 3y squared minus 4, dy dx, and then I'll let you figure out this is 0. Okay? Good. 1 is done. I've got 3 more for you in case you were wondering. Here we go. Next one, there's my vector field F, and the surface is the nose of the paraboloid z equals 5x squared plus 5y squared cut by the plane z equals 4. Direction is outward. Okay, let's rewrite our vector field. 3x, 3y, 5. And step 1, we're going to draw our surface. Our surface is a paraboloid. Okay. 5x squared plus 5y squared, and it's being cut by the plane z equals 4. So it just looks like a bowl. X, Y, Z. I'll say that's z equals 4. That cut it right there. But it's open. We only have one surface in this problem. It's open. Okay, that's my surface. Now, we have to decide what plane we want to integrate it over. I suggest we just project it over the xy plane and figure out what this circle's equation is. How does that sound? Okay, so let's project that surface over the xy plane. So I need to figure out when the plane intersects my surface, which would happen when z is 4. So when 4 equals 5x squared plus 5y squared. So hopefully you can tell it's going to be a circle whose radius is 2 over rad 5. Very good. So let's draw the base region. Although you know what, when it's just a simple circle, maybe you don't need to, huh? Yeah. Oh, get it straight, Professor V. Okay, here's x, here's y. Here's the base region, the radius 2 over rad 5. You know, we haven't decided yet, but I feel like we're not going to actually integrate in xy over a circle. We would go polar, wouldn't we? Yeah, so r would vary from 0 to 2 pi. We have the theta would go 0 to 2 pi, and r would go from 0 to 2 over rad 5. Good? Okay, perfect. Next, we have to determine n. Okay, again, our surface z is a function of x and y. So our options for n are negative partial with respect to x, negative partial with respect to y, 1, or partial with respect to x, partial with respect to y, negative 1. How do I know which one? Draw your stick figure, and you need to pretend it's you, actually. Let's make this personal. You need to be outside the surface, okay? So go to the extreme right here, and for you to be outside of the surface, instead of inside the surface, your head has to be pointing downward. So your head is pointing in the negative z direction, which means this is my vector that I'm going to use as the one that's normal to the surface for outward orientation. Okay, perfect. So my surface's equation is 5x squared plus 5y squared. So n is going to be partial with respect to x, partial with respect to y, negative 1. Perfect. 3, you're going to find f dot n using only x's and y's. Remind yourself, only x's and y's. So f was 3x, 3y, 5, dotted with 10x, 10y. Oh, we already only have x's and y's. That's easy. 30x squared plus 30y squared minus 5. Good? Perfect. Now we integrate. So flux is going to be double integral over s of f dot n ds, which is double integral over d of 30x squared plus 30y squared minus 5 dA. But are we actually going to integrate over the xy plane? We're going to switch to polar coordinates. So then now I'll say we're going to integrate from 0 to 2 pi, 0 to 2 over rad 5. Now this is 30 times x squared plus y squared, right? So that's 30 r squared minus 5, and dA is r dr d theta. Okay, perfect. From here you should be home free. Make sure you can get 28 pi over 5, and that's it. You can totally just slap a 2 pi on the integral and go from there. All right, nice. Are you getting the hang of it a little bit more? Okay. Hopefully the 4-step process helps it feel less chaotic. That's what everyone said in class yesterday. They were so happy. Okay, here's my vector field. I always like rewriting it just in component form without the unit vectors. Okay, x, y, y, z, 1. Exactly. S is the cap from the sphere, x squared plus y squared plus z squared equals 16. That's cut by the plane z equals 3, direction outward. So I feel like we should solve for z because we're also cutting it with the plane z equals 3. So z equals square root. I'm just going to take the positive radical if it's being cut by the plane z equals 3. So we have a sphere, radius 4, being cut by a plane. Yes, it's going to look like a little cap. X, Y, Z. So say here's 4, 4, 4. Okay, so here's the sphere. And then a plane comes and cuts it at z equals 3. So you could imagine it's going to come through, slice it, make a little circle. And the surface is just the top part here, just this cap. Okay. Good. I kind of hate this picture. Hold on. Okay, I swapped it out for a less disgusting one. All right, so here's my surface, S. Where do you want to integrate it? I'd say over the xy plane, right? Use xy plane projection or as the base. So let's see, it's going to be a circle in the xy plane, but I don't know what the radius is. How would I find it? I need to see where z equals 3 intersects my sphere. Exactly. So x squared plus y squared plus 3 squared is 16. That means x squared plus y squared is 7. Exactly. So in the xy plane, the projection of my surface, like if you're standing at the top of it and you're looking down, all you see is a circle, right? You see a circle whose radius is what? Square root of 7. Exactly. So I'm thinking we're going to go polar again, don't you? Theta 0 to 2 pi. R 0 to rad 7. That's rad 7. Okay, perfect. Now we need to determine n. So here's my surface. It's a function of x and y, the way we've set it up. So n is either going to be negative partial with respect to x, negative partial with respect to y, 1, or n will be positive partial with respect to x, positive partial with respect to y, negative 1. Which one is it? Well, you got to stand on the surface and you have to be outside of the surface. Where's your head pointing? Upward. So the z component should be positive. So this is what we're going to use as the normal vector. Okay, so remember your surface z is square root 16 minus x squared minus y squared. That's my f of xy. Let's take the partial with respect to x. Remember the shortcut I taught you when you have to do chain rule with the square root function? So you put 2, the OG square root in the denominator, and then you multiply by the derivative of what's inside up top. That would be negative 2x. So this will be negative x over square root 16 minus x squared minus y squared. And then similarly, partial with respect to y would be negative y over square root 16 minus x squared minus y squared, right? Very good. Now from here, If I find n is negative partial with respect to x. So it would be positive x over square root 16 minus x squared minus y squared. Positive y over square root 16 minus x squared minus y squared. And positive 1. Good? Okay, step 3. We need to find f dot n using only x's and y's. Remind yourself always, okay? So what was f? F was xz, yz, 1. And we're dotting it with, I want you to notice something. Rad 16 minus x squared minus y squared is what? It's z. So I'm dotting it with x over z, y over z, 1. That works out conveniently because then xz times x over z is x squared. Next component, y squared plus 1. Beautiful. So we knew we were going to go polar. Things are just falling into place beautifully. So step 4, flux is going to be double integral over s f dot. I rewrite this every single time. You want to know why? To remind me what the formula is. It can get so jumbly in the brain. You have Stokes' theorem, divergence theorem, definition of flux as a surface integral, definition of work as a line integral. I mean, it can swim around in the brain. The more you rewrite it, you're just going to keep everybody straight. Double integral over d. X squared plus y squared plus 1 dA. Then we go polar, people. We go polar, 0 to 2 pi, 0 to rad 7. This is r squared plus 1, r d theta, and you should get 63 pi over 2. You notice all the integrals are very relaxing, little polynomials. No one's making you do by parts or anything wild because the setup is really where it's at. The setup is the beef of the problem. Okay. Last one actually involves two surfaces, and the surface is not a function of x and y, so I thought it was good to round it out. So here's my vector field. Let me rewrite it as 0, y, negative z. Here's my surface. It has two parts to it. It's the paraboloid, y equals x squared plus z squared, y between 0 and 1 inclusive, and the disk, x squared plus z squared less than or equal to 1. Y equals 1. So we are going to have to do two surface integrals and put it together to find the total flux. Okay, let's start graphing. Now this paraboloid, since y is isolated, will open along the y-axis. Yes. And then it's only between y is equal to 0 and 1. And then the disk is basically like going to close it up. It's going to close it up. Yeah. So if you know divergence theorem already, you could find the flux that way. Okay. We're going to pretend this is 1, as is this. Okay? So I'll color it two different shades or colors. That way you can distinguish the surfaces. So that's surface 1, the paraboloid, y equals x squared plus z squared. And then this is surface 2. Okay. So what is surface 2's equation? Surface 2's equation is y equals 1. It's actually a plane at y equals 1, but when it intersects the paraboloid, then it makes this disk, x squared plus z squared is less than or equal to 1. So it's that disk at y equals 1, but really, who is this surface? This is y equals 1. X squared plus z squared equals 1 is the intersection right here, the boundary, okay? So two surfaces. Surface 1, we're going to find flux. Surface 1, we'll do the paraboloid, y equals x squared plus z squared. Okay, I have the 3D drawing there. We have to choose what plane we're going to project it over to use as our integration region. I say let's project it over the xz plane, right? Then you'll just have a nice little circle. So my surface S1 projected over the xz plane will give me what? A circle of radius, that's right, 1. Okay, very good. Circle of radius 1. That's basically here. Okay, you're pretending you're standing basically over here looking down at the surface. So radius is 1 for this circle. Okay, now let's figure out what n should be for surface 1. So you're standing on the surface. You can stand anywhere, okay? You could stand here. You have to always be going outward, but I'm trying to determine what the normal vector is going to look like. And here's my choice. So since my surface, this is where it gets interesting. Surface y is a function of x and z, you have two options for your normal. Are you ready? Yes, you're going to have partial with respect to x, negative y, partial with respect to z, or you're going to have negative partial with respect to x, positive 1, negative partial with respect to z. Since my surface is a function of x and z. So then the y component for the normal is either 1 or negative 1. All the other ones we did, it was z. So I wanted to show you what happens when it's different. Okay, so look at you. You're standing here. Yeah, you could stand here, but is that going to tell me if y is positive 1 or negative 1? It's more obvious right here at the extreme. That's why I always have you draw, at the min or the max of the surface. So here, where is your head going? Where is your head going? In the negative y direction. That's right. So this is the normal that we're going to use. Right here. N. My surface's equation is x squared plus z squared. So n is going to be 2x negative 1, 2z. Perfect. All right, now step 3, we're going to find f dotted with n, and we can only use what variables? X and z. Look at your 2D picture. We're only using x's and z's. Okay, so f, where are you? Over here. F dot n. Okay, let's go for it. So that'll be 0 minus y minus 2z squared. Don't have a panic attack. You go, oh no, there's a y. What do? You come through and you replace y with x squared plus z squared. No big deal. We got this. We got this. So negative x squared minus z squared minus 2z squared is negative x squared minus 3z squared. That's f dot n. Perfect. Okay, set it up. Here we go. So for flux 1, I'll say is surface integral for surface 1, f dot n ds would be double integral over d1 negative x squared minus 3z squared dA. You guys, we can go polar even though we're integrating over a circle in the xz plane. So x will be our cosine theta, and this time z will be our sine theta. It's totally fine. It's totally fine. Okay, let me take the negative out, and then we're just going to go 0 to 2 pi, 0 to 1. X squared is r squared cosine squared theta plus 3 r squared sine squared theta. Very good. And then dA is r dr d theta. Got it? Okay. From here, I'll let you work through everything. You should get negative pi. Perfect. Perfect. Now we have one more surface to do. Yes. Surface 2. Surface 2, what is the equation of surface 2? Y equals 1. Remember we talked about y equals 1 actually determines this surface. It's just bounded by this disk, okay? Very good. So what are we going to project it over? I think we should also project this surface over the xz plane. Same situation. Okay. So we can just say we're going to do same projection as above. So we don't have to do any extra work for that one. Okay, that's step 1. Step 2, we have to determine n. Okay, I'm going to go back to the picture. Now you're standing on surface 2, you have to be out of it. You have to be here, yes? Which way is your head going? In the positive 1 direction. Very good, positive 1y. So since it's just a plane, the normal is 0, 1, 0. If you don't like that, you could say, okay, y equals 1 is a function of x and z. So you know normal would be negative partial with respect to x1, negative partial with respect to z. But if you take the partial with respect to x and z of 1, you're just going to get 0. So if your surface is just a plane, it's easy to find n. Good. All right, step 3. We have to find f dot n using only x and z. So what was f? 0, y, negative z, dotted with 0, 1, 0. 0 plus y plus 0. So it's just y. Oh no, that's not involving only x's and z's. It's all good. We're on the surface y equals 1. Oh, so then that means f dot n is 1. Perfect. Okay. Step 4, set her up. This is flux 2. Flux 2. I don't know if it's legit to put a subscript on the flux symbol, but I know you put S2 all the time. F dot n ds. So it's going to be double integral over d2, which is actually the same as d1, whatever. 1 dA. So we actually don't even need to set up the integral or evaluate it. If you have double integral dA, that's just area of d2, which was a circle, radius 1, so it's pi. So the total flux is negative pi from the first surface, positive pi from the second surface, which is 0. So what does that mean exactly? Well, remember, flux measures the total flow of a vector field through a surface. So basically, since the total flux is 0, that means the amount of fluid flowing through this permeable surface is 0. Why is that? Because the fluid that's being pushed out through one surface is the same amount that's being pushed in or sucked in from the other surface. Okay? All right, I hope this 4-step process helped clear things up, and I hope it's easier for you to find the normal vector. I think this is one of the trickiest sections of this unit. It's way easier to find flux when you use divergence theorem and triple integrals, but that's only for closed surfaces, so you could have actually used it for this last problem. And there is a workaround if you want to still use divergence theorem when it's not closed. You just have to find the flux on the additional surface and then subtract it, but not always worth the time, you know? Okay, if you need more help with Calc 3, you're in the right place. Check out the rest of the video lectures that are on this channel. And I also have other video lectures for Calc 1, 2, differential equations, and so much more. Don't forget to give the video a thumbs up, comment down below, subscribe if you haven't already, and I'll be back sooner than later with new